Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting outward, far beyond anything familiar, and to the most distant reaches of the cosmos, toward galaxies so remote that the light reaching us now began its journey long before the Earth existed. Distant galaxies are not merely beautiful, they are records. Each one holds a chapter of the universe's biography, a window into a time when the cosmos was younger, hotter, and still learning what it might become. Some blaze with the energy of youth, others glow with the quiet warmth of age. Together, they trace the long arc of how everything came to be. If these gentle journeys bring you comfort, a like or a subscription helps others find their way here too. But right now, there is nothing you need to do. Let your shoulders drop. Let your breathing slow. Let your thoughts loosen their hold. Close your eyes if you like, and come wander the universe with me. Let's begin. Harold Verst, Time. Distance is time. The farthest galaxies we can see are also the oldest. When a telescope catches their light, it is receiving a message that was sent when the universe was still young. Distance and time are braided together out here. Nearby galaxies show us a calm, mature cosmos. Distant ones show us its restless early years, when everything was smaller, hotter, and still taking shape. Astronomers build a kind of timeline from this. They compare galaxies at different distances, looking for patterns that shift with age. You can watch the first heavy elements spread through space from dying stars. You can watch ragged, irregular shapes slowly settle into something more ordered. It is history written in light, and the pages are still arriving night after night, right on schedule. Before our sun existed, some of the galaxies we observe shone long before our own sun was born. Our sun is only about 4.5 billion years old. Many distant galaxies we study are so far away that their light began traveling toward us before the solar system existed at all. In that earlier era, the Milky Way was still assembling itself, and many of the heavier elements we take for granted had not yet been forged. Early stars had to do that work first, fusing lighter atoms into heavier ones deep inside their cores, then scattering those materials through space when they died. Those enriched atoms later became planets, oceans, and living things. When you look at a galaxy from that earlier time, you are seeing a universe that had not yet learned how to make a world like ours. That is what makes distant galaxies feel so profound. They are a view of everything that had to happen before we could ever arrive. A patch of sky that looks completely empty to your eyes can contain thousands of galaxies when a telescope stares long enough. They gather faint light, one photon at a time, stacking hours of exposure until whispers become visible. In some of the most famous deep field views, the region of sky captured is no wider than your little finger held at arm's length. Yet within that sliver, you can find spirals, ellipticals, and tangled irregular shapes, each at a different distance, each at a different stage of life. Some are close enough to show detail, others are barely a blush of color. Together, they reveal something startling. The universe is not sprinkled with galaxies, it is saturated with them. Once you know that, the night sky never feels empty again. On the larger scales, gravity can act like a natural telescope. A massive galaxy or cluster sitting between us and something more distant can then space so strongly that the background light is forced to travel along curved paths. The result can be arcs, doubled images, or near-perfect rings, not artistic distortions, but maps of invisible mass. By measuring exactly how that warping looks, astronomers can weigh the lensing object and trace where its matter sits. even when most of it emits no light at all. Sometimes the lensing also magnifies the background galaxy, making an otherwise unreachable system bright enough to study in detail. Gravity becomes both filter and spotlight, helping us see farther than our instruments alone ever could. Sounds like a silver screen, right? The silver screen metal. But this happens to be a simple power for you. Sounds that the property of your early medium will be lower than the most bright silver screen ever existing. The universe expands, it stretches the waves of traveling light, pulling them toward longer, redder wavelengths. A galaxy that once shone brilliantly in ultraviolet can arrive at our detectors looking deeply red, or even invisible to cameras tuned for ordinary light. That is why infrared observatories matter so much. They are built to catch this stretched, ancient light. A reddish glow from a distant galaxy can also hint at age. Older stellar populations tend to burn cooler and redder than hot, newborn stars. Astronomers separate these effects by measuring light through multiple filters and comparing the patterns to models of how stars evolve over time. A simple color shift becomes a distance estimate and a clue about when a galaxy's stars first ignited. In the young universe, galaxies lived much closer together and their paths crossed far more often. Gravity pulled them into slow, sweeping encounters that could last millions of years. First came the tidal tugging, stretching out long tails of stars and gas. Then came the mixing, as orbits scrambled and clouds collided. These events did not always destroy galaxies, they often transformed them. A calm disk could be stirred into a thickened shape. Two smaller systems could merge into a single larger one. Fresh gas could be driven inward, sparking bursts of new star formation in regions that were previously quiet. When astronomers look far back in time, they find a zoo of distorted shapes that make perfect sense in a universe built by assembly. Collisions were part of the growth plan, and the galaxies we see today still carry the fingerprints of those ancient meetings. A galaxy actively forming new stars tends to glow blue, because hot young stars pour out energetic light. When star formation slows, those bright blue stars fade quickly, and the galaxy shifts toward the warmer tones of older, longer-lived stars. Astronomers measure these color differences through carefully chosen filters, then compare them to models of how stellar populations age. It becomes a kind of mood reading, but grounded in physics. Some galaxies are still in a busy building phase. Others look settled, like a town after the festival has ended. Even dust leaves its own signature, absorbing light in ways that differ from the reddening of old stars. With only a few bands of color, a galaxy can tell you whether it is busy, resting, or hiding something. Small galaxies were everywhere, and gravity kept pulling them together. When two met, their stars mostly passed through each other. Space between stars is vast, but her gas clouds collided and compressed. Meanwhile, fresh gas flowed in from the surrounding environment, feeding more star formation and adding mass. Repeated encounters could turn a loose collection of clumps into a larger, more organized system. Astronomers look for signs of this rapid assembly in the shapes of distant galaxies, in how their gas and stars are distributed. It is a story of construction under pressure, where the materials kept arriving and the blueprint kept changing. The 148, 6, B, 8. Oh no, no, I see 8. Rockets, cats. Protein is highly slow. Hidden behind dust. Dust is made of tiny grains, and it is remarkably good at blocking visible light. In a distant galaxy, dust can wrap around star-forming region. To an ordinary telescope, the galaxy may look faint and unimpressive. But in longer wavelengths, the story flips. Dust absorbs energetic starlight, warms up, and then re-emits that energy as infrared radiation. Instruments that can detect those wavelengths reveal galaxies forming stars at astonishing rates, even while they appeared dim in ordinary images. Dust did not merely decorate galaxies, it concealed some of the most active ones. By seeing through it, we uncover a more complete picture of how quickly galaxies could grow behind a curtain. Cosmic noon. There was an era when the universe was especially productive, a high point in star formation that astronomers sometimes call cosmic noon. Galaxies were rich with cold gas, and many were also interacting and merging, which helped compress that gas and trigger bursts of new starbirth. Over time, the frenzy eased. Gas supplies were used up, heated, or expelled, and the average rate of star formation quietly declined. The universe did not stop making stars. It simply became more measured, more selective. Knowing when that peak occurred helps explain why many massive galaxies today are filled with older stars, and why the night sky contains a kind of relic warmth from a much brighter past. One frame, many eras. A single telescope can act like a storyteller with many chapters open at once. In one field of view, a nearby galaxy might show crisp spiral arms and active star-forming neighborhoods. In the same image, a more distant galaxy appears smaller and rougher because we are seeing it at a younger point in cosmic time. The instrument has not changed. The light has. Different distances mean different ages, and the camera records them all together. It is like holding a portrait that includes infants, adults, and elders side by side. That mix makes patterns easier to trust and surprises harder to dismiss. One observation becomes a cross-section of cosmic evolution. They can look like a soft fingerprint on black velvet, yet that faintness is not smallness. It is distance. Light spreads as it travels, and the galaxy's glow is diluted across an enormous sphere of space. Astronomers pull meaning from that faint impression by measuring its shape, its color, and how its brightness changes across the image. From those clues, they estimate how many stars must be present to produce what they detect. A tiny blur can represent a city of suns. The universe hides its grandest crowds inside its quietest specks. When gas falls toward it, the material spirals into a hot, crowded disk, and friction heats that disk until it shines with staggering power. The light can outshine the entire host galaxy, turning the core into a beacon visible across billions of light years. This is how quasars announce themselves. They are not powered by nuclear fusion like ordinary stars. They are powered by gravity, converting infalling matter into energy with remarkable efficiency. If the brightness fluctuates over weeks or months, that flickering hints that the glowing region is extraordinarily compact. When you spot one of these brilliant cores, you are witnessing a galaxy with an active heart, feeding and blazing in the dark. It still contains stars, and those stars keep shining for billions of years. What has changed is the arrival of new ones. The supply line has been cut. Sometimes the galaxy has used up its cold gas, that says, it may burn as a star of gases and stars. Sometimes that gas has been heated so it can no longer collapse into new stellar nurseries. Sometimes energetic processes in or around the core prevent fresh fuel from settling. The result is a galaxy dominated by the warm glow of older stars, with nothing bright and young to refresh it. Astronomers identify these systems by their colors, their spectra, and by the absence of the signs that point to active star birth. Quenching marks a turning point in a galaxy's life, the moment it stops adding new voices and begins to age gracefully with what it already has. Spiral galaxies feel like a late, polished outcome, something that should require time and stability to develop. That is why it can be startling to find spiral patterns in the distant universe, when everything was younger and more chaotic. Spirals are not painted on. They are patterns that emerge from motion as stars and gas orbit in a rotating disk. Seeing them early suggests some galaxies found their balance faster than expected and raises questions about how they managed to stay stable in such a rough neighborhood. Astronomers study these early spirals to learn how disks survive turbulent beginnings and to understand how the familiar shape of our own galaxy might have started forming long before the solar system ever existed. Clumpy young galaxies. Instead of neat spiral arms, many distant galaxies look like scattered islands of brightness. Those bright patches are enormous star-forming regions, far larger than anything typically seen in nearby galaxies. Early galaxies held huge reservoirs of gas, and that gas could become unstable under its own gravity, breaking into massive knots. Inside each knot, new stars could ignite in fierce bursts. Over time, these clumps can move, merge, and migrate inward, reshaping the galaxy's structure. They are not random noise. They are the visible marks of a young galaxy doing heavy lifting, converting raw material into starlight in oversized workshops. When you see a clumpy galaxy, you are catching growth in action, not a finished design. I have a solid wave. Compact and dense. Some distant galaxies look small, yet their gravity tells a different story. They pack the mass of an enormous galaxy into a region only a fraction of the expected size. Stars are crowded, orbits are fast, and internal motions can be extreme. These compact systems may be early versions of today's giant galaxies, caught in a brief, intense phase before they puffed up through later growth. How did something so dense form without tearing itself apart? Did it collapse rapidly from a rush of gas, or did early mergers funnel material inward? Compact galaxies are like cosmic pressure cookers. They show that the universe can assemble huge structures quickly, and that size alone is not a reliable guide to importance. Giant elliptical galaxies can look smooth and serene, as though they have always been that way. Their histories are often the opposite. Repeated merges can scramble stellar orbits, erasing the tidy rotation of a disk and leaving stars moving in every direction. Over time, that mixing produces a rounded, featureless glow. In some ellipticals, you can still find faint shells or ripples in the light, leftovers from past encounters, like wrinkles that never fully smooth out. Ellipticals also tend to host older stellar populations, hinting that much of their star formation happened early, before the system settled into a long, slow decline. A calm appearance does not mean a calm past. Sometimes the smoothest galaxies are the ones that survive the most upheaval. Because they have fewer stars and weaker gravity, they respond dramatically to processes that larger galaxies can shrug off. Their gas can be blown out more easily, their star formation can start and stop in fits, and their chemical makeup can stay simpler for longer. That makes them valuable time capsules. Some dwarfs preserve evidence of the earliest star formation precisely because their histories are less blended than those of giant galaxies that have merged many times. Dwarfs are also thought to be common building blocks, the small systems that larger ones grow from, piece by piece. Often, the smallest galaxies keep the cleanest records. When a dwarf galaxy orbits a larger one, the gravitational pull can gradually stretch it apart. Stars are peeled away and form long, thin rivers that wrap around the host galaxy in luminous arcs across the sky. These streams are more than beautiful. They are evidence of ongoing assembly, a reminder that galaxies are still growing by capturing smaller companions. The shapes and paths of these streams also respond to the unseen mass of the host galaxy, helping astronomers map its gravitational field. Even after a dwarf is mostly dispersed, its stars continue tracing the ghost of its former orbit, writing the story of the encounter in a slowly fading loop of light. It is easy to feel like our galaxy is the main stage, because it is the one we live inside. But surveys have shown a bigger truth. Galaxies fill space in every direction, and even a seemingly blank patch of sky can hold countless remote systems. Each one is a self-contained world with its own history of star birth, chemical change, and gravitational drama. When we call the Milky Way an island, we are also admitting something humbling. Islands have neighbors, and seas can be endless. The night sky becomes a map of other places, not just other lights. And when you picture that scale, you also picture time, because much of that light began traveling before humans ever existed. Looking outward is a way of meeting the larger universe. Galaxies in groups and clusters. Many galaxies do not live alone. They gather in groups held together by shared gravity, influencing one another across billions of years. In a group, galaxies can pass close enough to stir up gas, bend outer stars into faint streams, and gradually reshape each other's futures. Some become dominant, some become satellites. Some are slowly stripped of their material over repeated encounters. Clusters take this to an extreme. A cluster can hold thousands of galaxies, along with vast reservoirs of hot gas and enormous amounts of unseen mass. Inside this environment, galaxies move at tremendous speeds, and close passes are frequent. That traffic can alter shapes, strip away gas, and leave some members with little fuel to form new stars. Between clusters lie cosmic voids, wide, quiet stretches where matter is thinly spread. These empty regions are not featureless. Their sizes and shapes encode information about how the universe expanded over time. Even emptiness, it turns out, has a pattern. The cosmic web. On the grander scales, galaxies are not scattered randomly. They outline filaments and sheets that connect clusters, forming a vast web stretched across the observable universe. Imagine bright beads on invisible threads. Those threads exist because matter flowed along preferred paths under gravity, guided by the earliest ripples in the young universe. Gas followed those same pathways, and gas is the ingredient that makes stars. So the web is not just a map of where galaxies are, it is a map of where galaxies can be fed. When astronomers survey huge volumes of space and plot millions of galaxy positions, the web emerges, a structure that is both beautiful and deeply informative, helping explain why clusters sit at filament intersections and voids open between them. Most of the attitude to most dark matter, the invisible scaffolding, most galaxies seem to sit inside a much larger halo of unseen mass. This dark matter does not shine and does not absorb light, but it exerts gravity, pulling ordinary gas into growing clumps and holding it long enough for stars to form. Without this hidden framework, many galaxies would struggle to assemble as efficiently as they did. The evidence comes from how galaxies rotate. If you could weigh only the visible stars and gas, many galaxies would not hold together. Their outer regions orbit so quickly that the visible material alone cannot provide enough gravity to keep them bound. Something extra must be present, a large, extended reservoir of mass surrounding the galaxy's luminous core. This conclusion is not based on a single galaxy or a single method. It appears across many systems and many techniques. Dark matter becomes the simplest explanation that fits the pattern consistently. The part of a galaxy we can see is like the lit windows of a city at night. The mass that actually shapes the city's gravity lives mostly in the surrounding darkness. When a massive object sits between us and a more distant galaxy, the foreground gravity can bend the background light into dramatic shapes, arcs, rings, and multiple images arranged around the lens. These forms are not random. Their curvature depends on how mass is distributed in the foreground object, including it's dark matter. By modeling those shapes, astronomers can reconstruct a mass map, and they often find that the visible galaxies account for only a small fraction of what the lensing requires. Lensing does not ask mass to glow, it asks mass to bend light. Each arc becomes a signature of hidden mass, written in starlight. Lensing can also magnify a distant galaxy so faint it would otherwise be unreachable. When a lensing mass focuses the light, the background galaxy can be brightened and stretched across the detector, making spectroscopy possible on systems that would otherwise be just a dot. Nature provides a larger aperture through curved space, and astronomers have learned to use it. Quasars as backlights. When a quasar's light crosses the cosmos, it does not travel through emptiness. It passes through thin gas between galaxies, and that gas leaves tiny marks in the quasar spectrum. Those marks become a record of what the universe was like along that entire line of sight, how much neutral hydrogen remained, how enriched the gas was by earlier stellar generations. Instead of trying to see that faint gas directly, astronomers let a distant beacon carry the evidence to them. Many quasars spread across the sky can build a patchwork view of intergalactic matter at different distances and times. It reveals when the universe became transparent to ultraviolet light, and how early structures grew, a clever trick that turns a brilliant faraway light into a probe of the invisible, jets, from black holes. Some active galaxies launch narrow beams of particles that race outward at near the speed of light. These jets can punch through the host galaxy and keep going, carving their way into intergalactic space for distances that dwarf the galaxy's own diameter. At the far ends, they can inflate enormous radio lobes, and the impact points form bright hotspots where the flow slams into surrounding gas. Those jets can also heat the gas within and around a galaxy, keeping it too warm and turbulent to collapse into new stars. In galaxy clusters, this heating can appear as cavities in the surrounding hot gas, clear signs that something powerful has pushed the material aside. A galaxy's future can be decided by an invisible thermostat, controlled near its center. How are the universe clears? Reionization. The universe clears after the Big Bang. Much of the universe was filled with neutral hydrogen gas that absorbed energetic light very efficiently. In that period, space was largely opaque. Over time, early stars and galaxies produced ultraviolet radiation that broke hydrogen back into ions, and that change spread outward in growing bubbles. Eventually, those bubbles overlapped, and most intergalactic hydrogen became ionized again. Once that happened, ultraviolet light could travel more freely across space. The universe had entered a clearer phase, one where light from distant sources can reach us without being absorbed along the way. Astronomers piece this transition together by combining evidence from distant galaxies, background beacons, and the cosmic microwave background. It is one of the universe's great phase changes, like dawn arriving across all of space at once. End of Chapter 4. Reading chemical fingerprints. When light is spread into a spectrum, specific gaps and bright features appear at precise wavelengths. These are produced because atoms and molecules absorb or emit light in exact ways. Hydrogen has its signatures, oxygen has its own, so do carbon and nitrogen, and many others. By measuring the pattern, astronomers can infer what a galaxy is made of, even one too distant to resolve individual stars. The spectrum also carries temperature, density, and motion, because lines broaden and shift as gas moves and conditions change. A faint smudge becomes a place with measurable physical properties. You can learn what exists in a galaxy by analyzing the light that reaches you, without ever going there. The earliest galaxies had almost no heavy elements, because stars had not yet had time to forge them. The richer ingredients for rocky planets and complex chemistry are built inside stars over generations, then scattered through space when those stars die. Early galaxies were operating with a much simpler chemical toolkit, and that difference shaped how quickly they could build structure, dust, and future star systems. Each new stellar generation raised the bar. Heavier elements helped gas cool more efficiently. Cooler gas collapsed into denser clouds and formed new stars more readily. Dust grains emerged, reshaping how light moved through the galaxy. The first stars were not merely bright, they were architects, quietly rewriting what their galaxies could become, generation by generation. In a small galaxy, gravity has a lighter grip, and that makes it vulnerable to powerful events. When massive stars end their lives in supernova explosions, the blast can heat surrounding gas, stir it, and sometimes push it right out of the galaxy. If enough gas is expelled, star formation slows because the fuel supply is reduced. This feedback creates a kind of natural rhythm. Small galaxies can form stars in bursts separated by quiet periods, rather than building steadily. Supernovae also carry newly made elements away before they mix, then the unique city will be provided with cognitive habits over 40% of the digital disadvantage. It is a form of galactic self-control, preventing small galaxies from burning through all their fuel at once. For a short stretch of cosmic time, a galaxy can behave as though it has pressed an accelerator. Gas that might have formed stars slowly is driven into dense pockets, and those pockets ignite with new star clusters. In distant galaxies, this can produce a brilliant infrared glow, as dust absorbs starlight and radiates it as heat. Starbursts do not last long. They burn through fuel quickly, and the winds and explosions they generate stir the remaining gas until the burst exhausts itself. That is what makes them so valuable to study. Catching one is like catching a thunderstorm. You learn what galaxies can do at their most extreme, and you learn what finally brings them back to calm. Collisions are often the trigger. When two galaxies pass close, gravity strips angular momentum from their gas and pushes it inward. As gas streams converge, they collide and compress. That pressure turns large, diffuse clouds into dense, star-forming knots. A merger is both a spark and a stopwatch, igniting star formation, then eventually providing the feedback that shuts it down again. In the 1990s, astronomers pointed a telescope at a tiny patch of sky that looked nearly empty, a risky choice because telescope time is precious. After days of exposure, the image came back crowded with galaxies, far more than most people expected. It changed intuition about the universe. Even the darkest-looking regions of the sky are likely filled with distant systems. The deep field made the universe feel less like scattered islands and more like a vast, populated ocean. It also gave researchers a way to study galaxy evolution across time, because the same image contained nearby galaxies and extremely distant ones side by side. It was a reminder that the universe rewards patience and that looking longer can turn emptiness into abundance. Later, the ultra-deep field pushed even farther, reaching galaxies so faint they were previously invisible. Faint often means far, and far often means early. The image became a deeper archive, filled with small reddish smudges, hinting at great distance and great youth. The picture of the early universe became richer, messier, and more realistic. Hence, the James Webb Space Telescope. The James Webb Space Telescope Webb was designed for a universe where ancient starlight has been stretched out of visible colors entirely. Infrared is where that light lands, and Webb's sensitivity there is extraordinary. It can detect galaxies that are both far away and intrinsically faint, including systems whose light would be swallowed by distance and dust using older instruments. Webb also carries spectrographs that read chemical fingerprints from very early times, turning tiny patches of light into places with measurable properties. Some early galaxies appear compact and intense. Others look extended and surprisingly structured, Each observation feeds back into our models of how galaxies assembled in the first chapters of cosmic history. Webb does not just extend our reach, it changes the questions we dare to ask. That's why we have a single thing that we see when we invent. Or, if you cross the mind, commit, Dob. Webb tools, better questions. As instruments improve, objects that were once anonymous dots become places with structure. A faint point can resolve into a shape. A shape can reveal a stretched arc, hinting at lensing, a compact core surrounded by diffuse light, or multiple clumps suggesting a turbulent stage of assembly. Spectroscopy adds another dimension, showing whether gas is rotating, flowing outward, or split into separate components. The object does not change. Our ability to interrogate it does. Each technological leap converts mystery into measurement, and each measurement opens new mystery. Many galaxies once classified broadly or dismissed as featureless become nuanced and surprising when the data improves. A dot is often just a galaxy waiting for better questions and better tools. Large surveys measure galaxy positions across enormous volumes, then add distance through redshift to build a three-dimensional map of the cosmos. When you move through these maps, filaments and clusters and voids come into view, structure that would be completely invisible in a flat photograph. The universe stops looking like a sky full of points and starts looking like a genuine architecture, something you could almost navigate. Those maps can also be compared with predictions from our best cosmological models. Gravity tries to pull matter together. Cosmic expansion works against that. Dark energy appears to make expansion accelerate. The balance between these forces leaves signatures in how clustered the galaxy distribution is at different distances and eras. Small discrepancies could hint at new physics. In this way, a catalogue of galaxies becomes a measurement of the universe's behavior over time. In the very early universe, sound waves traveled through the hot plasma of matter and light, pushing material outward in expanding shells. When the universe cooled enough for light to decouple from matter, those waves froze in place, leaving a faint preference for a particular separation scale in the distribution of matter. Billions of years later, that preference still lingers, a slight bump in how often galaxies are separated by a certain distance. It is subtle, and it takes enormous surveys to detect. But once measured, it becomes one of the most useful tools in cosmology, because that preferred scale is known from early physics. It acts like a cosmic ruler. When it appears stretched or compressed at different distances, it tells us how the universe has expanded between then and now, a sound wave from the infant universe, still quietly shaping what we measure today. Asken, the quiet ones. Some galaxies have almost no spiral arms, just smooth, even light, and a population of older stars. Spiral arms depend on how gas, rotation, and mass are arranged. If a galaxy has little cold gas left, or if its disk has been dynamically heated so stars move more randomly, the arms can fade and disappear. Some of these smooth disks live in crowded environments, where gas was stripped away, removing the ingredient that makes active star formation visible. Astronomers study them by mapping their rotation and measuring how stellar ages vary from center to edge. They look like galaxies in retirement, still rotating, still shining, but no longer drawing dramatic patterns across their disks. The absence of arms is not emptiness. It is information about history, full, and the quiet that can follow a busy past. An irregular galaxy can feel like a spill of starlight with no obvious symmetry. That messiness is often the point. Irregular shapes can come from tidal stresses, recent bursts of star formation, or a history of uneven gas inflow. In small galaxies especially, even modest events leave strong marks, because weaker gravity means easier disruption. Astronomers decode these galaxies by mapping where young stars are clustered, where gas is concentrated, and how different regions move relative to each other. Sometimes the brightest regions are not at the center. Sometimes the gas disk is twisted or offset. These are clues that something happened, even if the event was long ago. Irregular galaxies are also important because they resemble the kinds of systems that were far more common in the early universe, living analogues of youthful galactic behavior. When galaxies pass close, gravity can grab their outer stars like taffy, stretching them into enormous tidal tails that arc far beyond the main bodies. Tails can also serve as highways for gas, channeling material into new regions and sometimes triggering star formation along their length. In some of these tails, clumps of gas and stars grow dense enough to collapse into small, self-bound objects, tidal dwarf galaxies born from recycled material torn from their parents. Unlike typical dwarfs that formed inside their own dark matter halos, these newcomers are made from gas already enriched by earlier stellar generations. A collision can tear galaxies apart and also create new ones in the same act, like sparks thrown from a grinding wheel. Destruction and creation happening together. Inside a galaxy cluster, space is filled with extremely hot, thin gas. When a galaxy moves through that medium at high speed, it experiences a pressure-like wind that can push its own gas out of the disk, especially the loosely bound gas in the outskirts. In some observed cases, galaxies trail long streamers of displaced gas behind them, like banners in a storm. Stripping changes a galaxy's future. Gas is the ingredient for star formation, and removing it is like taking away the pantry. Over time, a galaxy that entered the cluster blue and actively star-forming can gradually redden and quiet down. It does not require a direct collision to be transformed. Sometimes, all it takes is moving through the right medium at the right speed. And all the wild, faint, fated stars. The previous faint disappears in the corner. I saw the frank, bright disappearing. I know the simple top south. I know the faint is faint in the background. It's similar to the rate top sound. Where is faint top sound? It's sometimes faint top sound is faint in the background. Instead of a bright core and sharp features, its light is spread thinly, like a watercolor wash across the sky. How can something so extended avoid collapsing into a denser form? One clue is environment. Many of these galaxies live in clusters where interactions and heating can reshape gas and slow star formation. Another clue is their dynamics. Despite their faintness, some ultra-diffuse galaxies can still contain substantial dark matter halos, revealed by the motions of their stars or by the globular clusters orbiting within them. The galaxy's light is thin, but its gravity can be strong. Each case helps refine our understanding of how starlight relates to mass. Some galaxies are still waiting. There are galaxies where the starlight is minimal, yet the gas reservoir is enormous. The usual process of gas collapsing into stars seems to have stalled. The gas can be too diffuse to fragment into dense clouds, or too low in heavy elements to cool efficiently enough. Some of these systems are discovered through radio surveys that detect neutral hydrogen long before the galaxy appears in visible light. They feel like galaxies that are waiting to begin, or galaxies that started and then hesitated. They serve as laboratories for understanding what star formation truly requires and what can prevent it even when raw material is abundant. If you want to understand why galaxies light up, it helps to study the ones that stay mostly dark. The inside-out story. A common pattern in disk galaxies is that the inner regions build up earlier, and the outer disk develops later as fresh gas settles at larger radii. This creates age gradients. Central regions tend to host older stars, while the outskirts are often younger and more actively building. Gas with higher angular momentum tends to settle farther out, so later arriving material naturally extends the disk. The result is a galaxy not built all at once, but in stages, the center maturing first, the edges filling in later, like a city that expands outward from an old, established downtown. What distant galaxies tell us about our own? We cannot rewind the Milky Way like a film. We live inside it, and we see it only as it is now. Distant galaxies solve that problem. By comparing galaxies across cosmic time, astronomers can infer how disks assembled, how bulges grew, and how star formation rose and fell across billions of years. Distant systems also show us what the Milky Way did not become. The galaxies that quenched early, the ones that grew into giant ellipticals, the ones that stayed small and irregular. Each faraway galaxy is a proxy experiment, a way to explore possibilities for our own past, using the universe's natural variety as a data set. The story of distant galaxies is in the most personal way, indirectly, the story of where we came from. Every new survey adds questions. Astronomy advances in a rhythm. A new survey pushes deeper, and suddenly the universe looks more crowded, more structured, and more surprising. A deeper view finds fainter and rarer galaxies. A wider view reveals how environments shape the story, from dense clusters to quiet voids. Each increase in sample size strengthens what we know, and it also surfaces the outliers that force new ideas. Sometimes the questions are about physics. How efficiently did gas turn into stars in the early universe? Sometimes they are about measurement. Is a distance estimate being distorted by dust or lensing? Either way, the map grows, and the edge of the map remains the most exciting place to stand. The universe keeps offering more detail, and each answer is an invitation to ask a sharper question next. Coming to rest. And so, we come to the end of our journey, and the universe feels a little wider than it did before. We drifted past galaxies that shine from ancient time, carried their light across distances almost too large to hold in the mind. We lingered near crowded clusters and delicate streams of stars. We watched gas clouds collapse into new suns behind curtains of dust. We felt the logic of gravity bending light into arcs and rings, and we sensed the deep pattern of the cosmic web, galaxies gathered along invisible threads like pearls in the dark. In all of it, there was that quiet feeling of perspective. Each distant glow is not just a place, it is a moment preserved, a message that traveled for billions of years to reach this night, this room, this moment of rest. Some galaxies grow through calm accumulation, some are reshaped by collision. Some blaze briefly with fierce activity at their cores, and some fade into a slower, older light. Together, they tell one long story of change, written across the whole breadth of space and time. If this journey brought you some peace, a like or a quiet comment before you sleep is always welcome. It helps others find their way here too. But now, you do not need to hold on to any of it. Let the ideas settle, like starlight sinking below the horizon. Let your jaw unclench. Let your shoulders soften. Let your breathing find its own gentle rhythm. There will be another journey waiting if you want one. Otherwise, simply rest here, in the calm that comes after the cosmos has passed through. Sleep well, and good night.